All right, this is Chapter 4 Summary Notes on Atoms and Elements and a little bit about the electromagnetic radiation that you see a diagram of here on your screen. We all know that electromagnetic radiation travels very, very fast, 186,000 miles per second, or 3 times 10 to the 8th meters per second in a vacuum. That means in space where there is no other air to impart or impede the flow of anything. All right, the only part that we can see in is a very teeny tiny part that runs from 700 nanometers to 400 nanometers. A nanometer is 1/1000th of a meter. All right, and that's in this range right here that I'm circling in red. Infrared and ultraviolet are on either side, ultraviolet being what we get from the sun, hence the sunglasses right there to signify that. Gamma rays are probably the most intensive rays, the most high energy rays that we have, and that's noted by the term down here on the bottom. If we looked on the left-hand side of the electromagnetic radiation continuum, we see that radio waves are the longest. They can be 10 to the 5th meters in length, all right, which means they're extremely long, extremely low energy, okay? Microwaves are in here in the middle that we're used to being in our homes and satellite dishes, and perhaps you might have an infrared lamp in your bathroom. It glows red, or sometimes you see those in hotel rooms. All right, so here's a couple of questions about this electromagnetic spectrum. Which has longer wavelengths, infrared lamps or medical X-rays? All right, so look at the top of the page to see where those things are located. Look at the shape of the wave, and I'm sure you can answer this just fine. Okay, longer wavelengths would be to the left, and that would be infrared. Here's our infrared lamp. Medical X-rays are way over here on the right. And they're so powerful that you might be using a lead apron to screen your body parts and protect them. All right, so you're not subjected to these X-rays. All right, the high energy, again, higher energy has to do with how many wavelengths pass by you in a particular time period. And if there's more that pass by you, the more energetic it is. All right, so again, let's find cell phone. All right, cell phone's right here. Okay, about just a little to the right of 1 meter. All right, and then ultraviolet rays, again, we just saw where that was located down here where the sunglasses are located. All right, so which one has higher energy? And it's the ultraviolet rays, because that's what can cause skin damage. Okay. All right, I wanted to show you a hydrogen spectrum because you can actually see hydrogen gas if you have a good pair of binoculars and you go out and you look for the constellation that kind of looks like this. And then there's 3 stars across the belt. This is the belt of Orion. And Orion actually has a cloudiness of stars, or a nebula of stars. If the pen will behave for me, I'll draw it for you. All right, I'll make it purple. So we can get a purple pen up here, and it's still not working. All right, let's try that. All right, it's much lighter than that, as you can tell by the hydrogen gas spectrum tube there on the left. But this is a stellar nursery. And there's lots of hydrogen gas there. So if you have a good pair of binoculars, Orion is rising in the east very, very early in the morning before dawn. So if you go out, you might be able to see it. And it will rise later and later in the evening. It's one of our winter constellations. But you can spot it early in the morning. And that's kind of an interesting thing to go out and look for. Okay. So the question here is, what does the emission spectra tell us about the electron's energy levels? Well, this hydrogen gas, here's another mock-up of it. If we allow the light to travel through a very narrow slit, and this could be something as simple as a piece of film that has a lot of straight lines in it. I'm erasing Orion to try to draw this other thing for you. All right, the spectral glass that it might be traveling through has lots of parallel lines very, very close together. And as they go through this, they can actually spread out and break down the wavelengths of light that make up the overall pink light that we see that's made of hydrogen. So we see a red line, we see kind of a greenish teal line, a blue line, and a purple line. This is hydrogen's unique spectra. All right, now hydrogen only has one electron, but that one electron, depending on how much energy is put into this hydrogen gas tube, can jump around. All right, and it goes up to higher energy levels, and it takes specific amounts of energy in order to do that. And that amount of energy is represented by the letter N. And N can be whole numbers of 1, 2, 3, and so on. All right, and it means a distance from the nucleus. So if we have an atom, and it has a nucleus, and then it has this electron here, if it gains some energy, it might jump up to this energy level. And then on the return trip, it will emit some light, like we see here in the diagram to the left. So much energy, a certain amount of energy has to be absorbed in order to do that. It starts at its ground level, it jumps up to a higher energy level, and when it returns, a photon of light is emitted, just like we see in the spectra. If we increase the energy quantity, it might jump out to another energy level, which means a higher energy level. And a higher energy means it has to go over to the right on that electromagnetic spectrum, and it might give off some blue wavelengths of light. Okay, so it depends on how much energy gets absorbed as to how much photon energy will be released in a colored wavelength of light. That's not to say it can't also emit other wavelengths of light that are not visible to us, in other words, the ultraviolet end or the infrared end. It can certainly do that as well. All right, so this is just an introduction to how electrons can give us spectra. Every element has a different unique spectra. All right, and in the next video, we'll talk about sublevels of energy on main levels of energy.